there. Technically, my title is CUDA educator. I'm more of an evangelist. I just like putting educator on my business card versus evangelist. Bit of a jack of all trades when it comes to CUDA, master of none. So I will try to answer your questions. If you have any deep technical questions, we'll defer it and just email me, and I'll find the right people to help you answer. I apologize when I'm a bit out of sorts. We do have our GPU Technology Conference started today. Been a crazy last couple weeks and weekend, and I'm going to go right back there after this and continue working all through it.
Thank you very much for your time on a busy schedule.
Yes. Yeah, and I think I did come off the bench for this one. I think there was another talk scheduled. So I try to get as many data mining, machine learning examples. I have a few of them in here to talk about. But there's definitely more out there. I can point you to the sites that have the information and hopefully give you what you're looking for. All right. Anybody not heard of Nvidia? You'd be surprised. There's still people. It shocks me. Even younger people. All right, so we'll just get to the intro Nvidia slide. All right, so the 3 points I'm going to get across in my talk today, it's going to be mostly a high level. I'm not going to get too deep technical in anything, so I just don't have time in an hour. I'll show you a lot of resources at the end, but the first thing is, what is accelerated computing? What do we mean by this when we talk about accelerated computing? Us, Intel, and pretty much everybody in the hardware industry is talking about it. And then I'll get into the why and how of GPUs, which is a specific type of accelerated computing. And then finally the resources, where you can go and learn more if this is something you're interested in for your technologies. Okay, so question, what is Moore's Law? Who wants to hazard a guess? Oh, come on.
Denser and denser, every 1.5 years.
Okay, pretty
Double by every 1.5 years.
Okay, yeah. So denser, you mean transistor?
Twice as years.
Yeah, so yeah, Moore's Law. Number of transistors double every 18 months to 2 years. My favorite quote of Moore's is, if Al Gore invented the internet, I invented the exponential. Because anything in the computer industry that has an exponential growth, people are like, oh, that's Moore's Law. No, just talking about the transistor. And we typically get the power will double every 18 months to 2 years. And we did a really good job keeping up with that for the first 40 odd years. This is just a simple graph of clock speeds over time. There's a whole bunch of different CPUs and processors over time. And you can see the first 40 years, we kept up with those transistors. Every time the transistors doubled, we were able to crank the clock and put a bunch of cool little tricks into the hardware and just get the faster speeds. But you can see, in the early 2000s, that we really just hit this wall, this brick wall. And I used to build computers, in the early mid-90s, and whenever I was going to upgrade, I was always trying to find a CPU with the best. Question?
Yeah, are you counting cache?
Cache?
Are you counting free cache?
No, this is pure just clock speed. What gigahertz is it running at? For a conventional processor. So like a 3 gigahertz, CPU, MIPS processor, whatever it is. This is basically just going through Wikipedia and finding all of processors over time and what their clock speeds are. And so when I was building computers, there's always which processor has the most gigahertz. I wanted the best. But now everybody's pretty much caught up. They're all the same. You can get, you see people overclocking to 8 gigahertz, but they're using like the liquid nitrogen to do it, and that's just not a scalable solution. People aren't going to be topping off their computer every time they want to play a game. So we really hit this wall. So processors just aren't getting faster. And me as a software guy, I used to always be able to rely on, if my code didn't run very fast, I'd just wait till the next processor come out. Maybe do a little tweaking here or there, but it would just run faster. So the days of that happening are over. Your serial processing just is not going to go faster. In the abstract, if you just wrote a single-threaded, very dumb app, you would use 1% of a modern, less than 1% of a modern CPU. That even though CPUs today have massive amounts of parallelism, you need hundreds of way parallelism to get any kind of speed. And a lot of this is being done for you by the compiler and the hardware. They're actually parallelizing your code underneath you, but that doesn't scale well, especially when we get into these massively parallel programs that we're talking about. So the brick wall, why we're hitting this is power. You can only drive so much electricity through those tiny, tiny transistors, where I think Intel's at 10 nanometers now or something crazy, in a really small package, and so you have to be able to pull that heat away before you burn up your transistors. So we just can't keep cranking up the clocks like we used to. It's like even in the mobile space, right? If you crank the clocks on your cell phone, the battery's going to die very shortly. So we just can't rely on that, just kind of brute force approach. There's the memory wall, just getting data onto the chip. If you don't have data, there's not much work to do. This affects all processors, CPUs, GPUs. This is why we find CPUs now with almost 3/4 of the die space as caches, L1, L2, L3 caches, because they're trying to solve this memory problem. And then finally, instruction level parallelism. This is, when I learned about this, I was always very amazed at what the hardware guys could do coming out of college. There's just all these tricks that they do in the hardware to basically make your serial code or slightly parallel code run faster. Things like try to predict the future. They look ahead and say that you see a branch, and if, whatever branch in your code, And they can either try to guess, say they have some free resources, they'll try to say, well, I think it'll take the true statement, so I'm going to go do that work ahead of time. So if we get there, then you just sped up the application. Or it can do both sides, or if you have instructions that can run in parallel. So there's all these little tricks that hardware has been doing for a while to make our code go faster. The problem is it's a super linear increase in complexity for a linear increase in speed, and it's just not maintainable. We're basically getting to the point where we're using more transistors to try to figure out our work and go faster than we have the transistors to actually do the work, and besides the ones that are being used by the cache. And so has been a crutch in the software world for a while, this trick. This is why our code does get faster a lot when we used to just buy the next processor. But it's where we're just running out of room to put this stuff. We have to use the transistors or something else. So how do we get past this? How do we get to exascale and continue doubling our speed every 2 years, which we've been doing a pretty good job of? And the answer is to go wider, to not go faster. The world is getting wider, it's going more parallel. And it's all about heterogeneous computing, accelerated computing, GPU computing, it goes by lots of different names. But it's really using the right processor for the job. It's not about getting rid of the CPU. The CPU does some things very, very well. It does task-based parallelism very well. It's really good at making a few threads go super fast. Whereas the GPUs and accelerators are good at massively parallel programs like data parallelism. You have tons and tons of data to go through. Or you have a whole bunch of, you're batching up stuff. You have a whole bunch of small programs you want to do at once, so you just have more throughput. When you think of a modern game, we do 1 billion threads a second on a modern game. I mean, just lots of these tiny little threads, and it's all about the throughput. It's the aggregate throughput, not the speed of an individual thread. So that's what heterogeneous computing is. Basically, a really simple idea. You write your code, you keep the serial stuff on the CPU, the stuff it does well, running the operating system, stuff that doesn't parallelize well, file system I/O, lots of that stuff keeps on the CPU. And then you move your compute-intensive stuff, your highly parallelizable part, which is, depending on the application, could be 5% to 20% of your application, where you have a bunch of tightly nested for loops where you spend all your time. That's what you move to the GPU, and they work in parallel, they work together. So 3 major accelerators out there. I'm just showing you the discrete version. There's different form factors of these. There's Nvidia on the left, that's our Tesla card. You notice it doesn't have a display. This is a card that's dedicated to compute. You can do compute with any of our ones that have displays. This is just one that people only want to use it for that, so why put displays in there? There's the AMD processors, ATI processors, GPUs in the middle. Used in this space, not as much, but people still do some compute on them. And then the Intel Xeon Phi at the far right. Recently new into the space. Again, it doesn't have a display. This is just purely dedicated at compute. I think the 1092 in China is built mostly off these, but it runs at like 23 megawatts. pretty beefy supercomputer. But the 3 major accelerators in this area. There are FPGAs. I left them off here because those aren't really general purpose. They're mostly focused on one thing, whereas these are kind of general purpose accelerators. But where are GPUs? GPUs are everywhere. This is obviously a marketing slide. From cell phones, we're at GPU, the GTC conference, we're going to announce more about our TK1, which is our next mobile chip. So you'll have a fully programmable, CUDA-capable GPU in your mobile devices coming out this year, so you can do all kinds of cool stuff with it. All the way up to the Titan supercomputer, the #1 supercomputer in the US. The top 10 greenest supercomputers in the world, the most perf-efficient ones, are all powered by Nvidia GPUs. That does the majority of the heavy lifting. Cars, you're basically not going to be able to buy a high-end car starting about in 2015 that doesn't have at least 2 of our processors in it, doing driver assistance, driving infotainment displays. So their GPUs are pretty much everywhere now, the whole spectrum. Right, so some examples of the benefits of going to GPU. This is a machine learning example. I think on the next slide I actually talk about what it is. But when they originally did this training, they were doing I'm not a machine language guy, so I apologize if I say things wrong, but they were doing the training of the neural networks, of the neural nodes. Running on 1,000 nodes in the GPU dense data center, something like 16,000 cores, running at 600 kilowatts, and it was if you added up all that hardware, it's a $5 million hardware. They've now moved to 3 GPU server racks for a total of 12 GPUs at a cost of $21,000 and 3.6 kilowatts to train in the same amount of time. So again, it's no longer brute forcing a CPU to do what it does not do well, and taking the combination of the two, which work really well together. And I think, here's the data on it. Just the training, getting the same results with 1.8 billion parameter set, basically trying an untrained visual recognition program, being able to see stuff in a static image and training it. And I'm not a machine learning guy, but I found it interesting when they went to 11 billion, they really didn't increase, they actually went down in the number of things it recognized. I thought that was an interesting data point. But the purpose of the slide was saying going from that massive supercomputer down to a machine that can just fit, basically under your desk with 3 server racks, and training in the same amount of time for much cheaper and much more perfect efficient. This is a medical example. I really like this one. I know it's not machine learning or data mining, but I just think it's a really cool thing. Open heart surgery, very scary operation. They give you a drug to stop your heart so that surgeons can actually get in there and work on it. You're on a bypass machine, and eventually they'll give the drug to say go, and sometimes the heart doesn't start, very dangerous thing. Most surgeons could operate on a beating heart. They choose not to because it's very, very hard. And only in life or death situations would they operate on a beating heart because it was too dangerous to stop. So they wanted to combine the best of both worlds, and this is a research project to do that. So what you're actually looking at here is there's 2 cameras looking into the heart, and actually instead of opening up the chest, they just drilled tiny little holes. And so this is a camera looking in, and that grid is superimposed on it, and that's the area the surgeon's interested in. And so the video on the right is that grid motion compensated to be virtually still. You can tell it's pretty close there. You see light coming through every once in a while on the video on the right. So it's virtually still. So that's what the doctor would actually operate on. He operates virtually or remotely, even though he's right next to the table, on the still image. And then over the patient is this robot thing with these 6 arms and these 6 little holes. And so it's just sitting there moving with the heart, based on what the camera's telling it, what's going on, depending on how the heart's moving. And as the surgeon's, cutting or stitching or whatever he's doing, that's translating to the robot and is doing it for him. So, or him or her. So
is that a Da Vinci machine?
It's very related to the Da Vinci machine. I think it's still in John Hopkins.
I know that the other thing that they do is they chill the entire body.
Yes, there are other, and it's not just heart surgery where this goes on. Yeah. So they use this for a lot of other things, not just heart surgery, but heart surgery is a tough one because they got that big beating muscle. And so, where was I? I lost track. Stomping. Oh yeah, and so it's, you could do this with a supercomputer. You could do this with a very large supercomputer, but those are kind of hard to hook up to an operating system room. Usually you only have one available, and so you don't have a lot of redundancy. But by going to GPUs and in the right heterogeneous computing, you're letting the GPU do all the image processing and all that massive parallelism. You can now have 3 servers underneath the operating system table for redundancy, so if one goes down, you can just fail over the next one and move on. This is actually a pig heart here. They're opening a human trial sometime very soon. The biggest thing that surgeons don't like about the system is the chest isn't already open. So if something goes wrong, it takes them a lot longer to get to the heart. But they are using it for a lot of other surgeries. So just a different kind of use of GPUs as opposed to just crunching data. All right, so those are a couple examples. I'll go through some more later. Hopefully that whet your appetite a little bit. So how do you actually use GPUs? How do you program these things? When it started off, Ian Buck, who was my boss, he invented this whole CUDA thing. It was his Stanford project. Essentially, he saw GPUs were getting more and more powerful in the gaming world, and he wanted to be able to use them to do his work because he couldn't get time on the supercomputer. And so at the time, him and Mark Harris and a few others were basically hacking DirectX and OpenGL to do their work. They were translating their data into vertex coordinates, writing pixel shaders to draw something, taking the red, green, and blue coordinate, or the data that came out, and then translating it back to their answer. Very complicated, very hard to do. And so he was like, well, why don't we just make a compiler that does this for us? So that was his Stanford project, Brook, which was a C compiler for CUDA. And that was early 2000s he was doing that, and that is what CUDA is now. Anybody know what CUDA stands for? Wrong. It's not an acronym. Unfortunately, some marketing guys got a hold of it early on in the day. And they said, hey, we should make this an acronym. Let's call it Compute Unified Device Architecture. Sounds cool, lots of buzzwords. But it's, Ian eventually, when he got a little higher up, was like, wait, it was just a name. I called it CUDA. And so it's not an acronym, although we capitalize it. We tend to capitalize everything, so that's why it's there. So it's just the name. It doesn't stand. And unfortunately, you'll still find Nvidia papers with that in there, just because that's what marketing was calling it. So that's what we're supposed to say. But we're trying to squish it, so it's just the name. So it was a C compiler. That's what it started off with. It was just CUDA C. So we still get that today. When I say CUDA, people are like, well, I don't want to write in C. It's a lot more than that now. There's a CUDA car, and this is actually where the name came from. Ian wanted to put a cool picture on his Stanford project, so he put the CUDA car in front. He was a fan of old cars, and so that's where he decided to get the name from, was CUDA. There's a beer. Here's a CUDA beer. When I was doing my university evangelism talks, I was trying to get the marketing guys to let me get like a little pony keg with stuff and carry around. Although I heard it's not very good. There's a wine. There's a CUDA wine. There's a coffee. If you search on Twitter for CUDA, you're going to get lots of very interesting results because it's shorthand for could have. And so it's actually really hard to find stuff on Twitter just about CUDA. Usually I have to put CUDA GPU or CUDA Nvidia to get some interesting results in Twitter. So what is it? What is CUDA? If we could do it in one slide, it's really become our platform for parallel computing. What it takes to actually program on our GPUs. It's the programming approaches, which I'll talk about briefly here through this talk. Our development environment, we have lots of really great visual tools. I mean, you're working with billions and thousands of threads, so you actually have to have visual tools to work with it, or it makes it easier. We open sourced our compiler toolchain on top of llvm. You'll see some of the languages I'm going to talk about, like CUDA Python was built on top of this. There's like the R statistical language is built on top of this. I have some examples on R. So we open sourced that about 1.5 years ago now. And then hardware capabilities. So I mean, GPUs are gaming devices first. The GPU industry is much bigger than the supercomputing world. I mean, as I was telling some of these guys earlier, when Call of Duty, and this was in 2012, Call of Duty, big AAA game title, when it was released in the first 24 hours, it made $700 million. When you think of like Black Knight or Dark Knight, the Batman movie, huge movie. It never made that much the entire time in box office. So the gaming industry is huge. It's so much money. And with all that money is where all this came from. All that innovation and competition really drove this. And it does continue to drive it. It's a cash cow for a lot of this industry. Intel, us, AMD, it drives a lot of this stuff. Even though supercomputing and high-performance computing is picking up, it's a lot about gaming. But we started adding hardware capabilities specific to computing. What we think the industry needs. Like one's dynamic parallelism, where a single thread of millions can launch a whole new grid of work. Whereas previously the CPU always had to babysit the GPU, had to keep launching more work. It's now possible for your GPU to do that. So that's like a hardware capability we added for high-performance computing. So in 2008, about a year after we released CUDA, our first general-purpose GPU called the G80, 77 supercomputing teraflops, not a lot. Not many people using it at the time. And we fast forward to 2014, and we have 41,700 supercomputing teraflops. You pretty much cannot find a new supercomputer being built that doesn't have some form of accelerator. And I think we're about 85% of that market. So a lot of people are making use of GPUs. Lots of people teaching it, using it to teach parallelism. ACM just released their CS 2013 curriculum guides for computer science. And the second most important key area was parallelism. As we see, you can't find a piece of hardware that doesn't need at least hundreds of way parallelism to get performance. And yet, if you go to 98% of the schools, and they may have one elective parallelism course. It's really bad in the computer science area. So if you know any computer science professors, go point them at this new curriculum guideline and say, you need to change because it's getting bad. We can't find people that know parallelism to program. It's getting bad. Anyway, sorry. Just tangent. All right, so how do you actually accelerate? 3 main ways. We believe this is for any accelerator, whether you're us, an Intel, or somebody else. I call it 3+. There's lots of applications out there already done. I think I have a list here. We know of 272 big name applications like Amber, NAMD, and all these guys that are already accelerated. You just have a GPU in your system, you give it your data, and it just runs a lot faster. You get your work done faster. You get more iterations done in the same amount of time. So lots of them out there. I think we'll have a list. I have a link here, nvidia.com/apps catalog. So this is the first step. Just let somebody else have done the work. Go download it and apply your data, and it just goes faster. So saying the application's not out there, you're designing your own code. Some performance numbers. It goes fast. So the application's not out there, or you're designing new code. Next one's libraries, drop-in acceleration. I mean, who here actually writes code? Okay, about half. So, I mean, you've used libraries before, right? You read the documentation, you call the API calls, and it does what it's supposed to. Many accelerated libraries out there. Some ninjas spent months and months getting code to run really well on all the different types of hardware. Just use it, and it goes faster. Go look for it. Don't reinvent the wheel. I always tell these people. Question?
Does that include Java?
Java, actually, it will. We are partnering with IBM, and so basically all their new supercomputers are going to have Teslas in them, and most of their stuff is built on Java, so they're in the process of getting Java CUDA working. Yes?
Support Ruby?
Question?
Ruby.
No
Ruby.
Ruby? No. Although there's some people definitely looking in like the JavaScript area and the Ruby area, but nothing yet that I'm aware of, other than maybe some research projects. Nothing viable. Yeah.
Could you elaborate on R? Because R is known to be.
Yeah, I'll go in a little bit more on R. Yeah, I just have a few examples, details on that. But yeah, don't reinvent the wheel. We see this a lot. People in the industry will come to us with some code problem, and after we break it down, we realize they're just rewriting matrix multiply. I mean, that is a solved problem. There's a library that does it really, really well on the GPU, CPU, whatever it is. So don't reinvent the wheel. Go look at libraries first. There's lots of them out there. Our philosophy is we build the building block libraries like cuBLAS, all your basic linear algebra stuff, cuRAN if you're doing kind of Monte Carlo simulations and you want random numbers. Nvidia NPP, our performance primitives, something like, I think we're at 5,500 signal processing algorithms, from anything from radio to image processing, whatever you want to do. There's most likely a library already out there for you. And so by building the building blocks, then the ecosystem, the third-party library writers can build on top of us. Like Magma, they have a much more dense linear algebra suite. And they also will try to make use of all the processors in your system, both CPU and GPU. You're doing that heterogeneous computing, so it's another library. There's Thrust. If you're going to do anything with C++ and parallelism, I highly encourage you to look at Thrust. It's basically the standard template library for parallelism.
Is C++ release 11?
No, this is not. ThrustWorks is just a library. We have stuff coming for C++ 11, not including 6, but coming soon. So Thrust, yeah, you're not writing GPU-specific code that's compiled to both OpenMP and Intel Thread building blocks, so it's very portable, but also compiles to CUDA on the back end. You can write your own back end if you have FPGAs as well, but it's a really great way to quickly get parallelism in prototype code. You just have device vectors, host vectors, and then you can do transform, reduces, sorts, all these little algorithms that you need. So here's R. This is using the R compiler and our cuBLAS library. We actually have a new one called NVBLAS, which is API compatible with the CPU version. So all you have to do is change the library you're calling. And what we're doing here is we just dynamically loaded our NVBLAS library. And then this is scaling. So this is just a single CPU, but it's showing you that with 4 GPUs, 4 K20X GPUs, which is not our highest end, but pretty high, the NVBLAS will automatically use multiple GPUs. So if it's in your system, it just spreads the work around. You don't have to do anything. So here, this code would work. If you just got rid of that line, it would just run, and then you add this line, and it's just drop-in acceleration for R. So things just go a lot faster. And we're trying to do that a lot now with our libraries, make API compatible. So it really is drop-on. You just change the library you're calling. Question?
I'm going to post the slides.
Yeah, I think we.
I'll take a copy and post them.
Yeah, so the slide.
The name of the library is NVBLAS.
Yeah, NVBLAS is the API compatible version. It calls cuBLAS underneath, which is our basic linear algebra library. So NVBLAS is kind of a wrapper for that. But yeah, question?
So this is literally just a straight drop-in.
Yeah, so all you're doing is
implementation.
Exact same code for BLAS.
Like OpenBLAS or MKL or something.
Yeah, you're just changing the library you're calling. Yep.
Nice.
NVBLAS. I think it does. I would have to look at the documentation. I think it supports the vast majority of the calls. There may be a few ones that don't make sense, but again, it's multi-GPU support. So if you have multiple GPUs, it just spreads that work around. Because the whole point of parallelism is if you add more processing, you just go faster. So I was told to talk a lot about R. So some of my examples. Yeah.
So if I did that on my MacBook, will it make the MacBook unusable for me for the rest of the processing, or
Are you talking about for the graphics, like freezing up the display?
Can you repeat the questions for the video?
Yeah, sorry. So the question is, if he does this on his Mac, will it make it unusable or break down? So if you're processing on the GPU that's also driving your display, the display is going to get priority there, and so it would not run as fast as it could if you had a discrete GPU that's not driving the display. I mean, it wouldn't because it's a separate processor. You're just offloading the work. Does that make sense? So we have a link out there. All the libraries we know about that are accelerated on the GPU, we try to put most of the ones that we've looked at, even the ones that aren't ours, on there, so you can go look through there and see the library supports your need. All right, so that's libraries. That's drop-in acceleration. Start there when you're developing new applications. Next up is directives. Anybody done OpenMP programming? Just the eBay guy. All right, so OpenMP is directive-based programming. You're not actually modifying the underlying source, and this is for C, Fortran, and some C++. You're actually just giving hints to the compiler. They're basically pragmas in C, or a specific type of comment in Fortran. And so you're telling the compiler to do work. And so if the compiler doesn't understand the directive, it'll just ignore it and move on. So it's very portable. I think I have an example here yet. So this is Fortran. And so like in this case, you have a couple nested parallel loops where you know you're spending most of your application time and you think it's parallelizable. You just put this hint in there and the compiler go in and try to parallelize it for you. So you're not actually writing the accelerated code, you're like compiling it for you. It allows you to control some data movement, how the data is moving around between the two processors, but it's very little amounts of work. Like we have great cases of people taking 30-year-old Fortran code, adding in like 20 lines of code and getting like really big speed ups just because they're not having to rewrite anything, and then they can just go back to their old compiler and it just works.
Is there something like this for Python and R?
There's a little something about Python. I'll get to that. Remind me if I ask later, because I don't think I actually have a slide, but there's something similar. You know vectorize?
Yeah.
There's a thing, which I was telling wherever we went, but you know Continuum Analytics, the
Yeah.
company? They do some SciPy, NumPy.
Yeah.
They have, in both their Numba and Numba Pro Python compilers,
Right.
they actually compile those vectorized functions to machine code. So it's similar. It's not quite the same, but it's similar, where you're letting the compiler do the work for you.
And again, something for Java?
Java, nothing yet. I mean, we're still working on Java with IBM. I mean, this is a great way, especially if you have existing code or you want to prototype. And again, it's C, Fortran, and a little bit of C++. Getting better with C++ because it's just a very hard language to do with this approach. But you can get very quick acceleration and not have to do the work. And it's very open and portable. It targets all the major accelerators. It's an open standard. They actually plan on merging with OpenMP again at some point, but it's just a little ways down the road, hopefully. So this is Saxby and OpenACC. Since single precision A times X plus Y, just basically simple for loop, 0 to n minus 1, A times X plus Y. And all you're doing is adding that one ACC parallel loop and just saying, hey, compiler, go parallelize this for me. And that's all you have to do. You didn't actually write any GPU code. If you know OpenMP, that's what it looks like in OpenMP, very similar. There's three major vendors. They're all commercial vendors, CAPS, Crane, PGI, that support this. GNU is going to add this to, or Linux is going to add this to the GNU compiler, GCC. Hopefully starting to come out end of 2014, so it'll be open source and free, whereas these other three are pay for compilers, but they all have trial licenses, so you can at least try them out. But moving into the open source space. The 2.0 spec came out last November, huge improvement over the 1.0. So if you're going to be working on this, make sure you do the 2.0 stuff. Just makes life a lot easier. So that's directives, and again, these all work together. Is the great part about this. So that's what we try to tell people: start with libraries, then go to directives if you're in C, Fortran, C++, and then once you get stuff running there and you really want to hand tune, that's when you get into the actual CUDA-enabled programming languages. What we'll talk about next. Lots of them out there, not an exhaustive list, but these are kind of the major ones. There's C++, Fortran, Python, F#, if anybody does any finance stuff, F#. MATLAB has a lot of GPU support with their parallel computing toolbox, where instead of array, you do GPU array, and the rest just kind of works. There's Fortran is the R language. I think I have some examples of coming up here next. Yeah, so here's RG. This is the GPU version of R. Again, I'm not an R expert, so I stole these slides. I apologize. So they just basically took our llvm compiler and built R on top of it. You can dynamically compile the code to run on the GPU. Yeah, that's how we created DSL. So here's some actual code. So people who know R probably know this a lot better than I do. So you're creating some sort of vector. You're doing a DB, which I don't know what that is. Anybody know what a DB is? R guys? But I know this is R code. Instead of just RG, you just have R. And so you're just changing what you're calling. And these are just functions that are accelerated, and it'll just start running on your GPU and processing. So I think people who know R.
Is that RG, is that a plugin on R? Is that?
It's a different compiler. So you just have an a GPU-enabled compiler, or CUDA-aware compiler. That knows how to work.
Copying to device memory?
Yes, probably. Yeah, that would make sense. It's copying to device memory, yeah. And then applying whatever that function is to it.
The G-apply is probably like a graphics CPU apply.
Yeah.
There's list apply and
Okay.
other types of things.
Yeah, and so we have this, a bunch of information on this on our webpage again, so I just never written in R, so.
So,
Question?
in all of these applications, I remember last time I programmed with CUDA, like you have to specify the number of threads to use, the thread blocks and all that. All these applications, they implicitly figure out what to do? Or?
Yeah, so the question is in CUDA languages, especially earlier, you had to specify how many threads you're going to use in our terminology, thread blocks and threads. So in C and Fortran and those lower level languages, that's still true. We're looking at ways to remove that restriction, accept it as like an optimization. Techniques like OpenACC, you don't have to do that. The compiler's trying to figure it out for you what the best one is. You can still go in there and tell it and optimize it, but you don't have to specify it.
And that is regardless of the specific GPU we are finally going to run the binary, or? Is it
Yeah, that's regardless of the specific GPU. So usually in the production world, you want to query the GPU and then determine the right number for the threads and blocks. Because GPUs are different, just like CPUs, you use different parameters for things. But yeah, OpenACC is trying to do that for you based on, it'll see what you're targeting and try to actually figure that out for you. But we're looking at ways to get rid of that in the C and the C area, so it's easier to get started, but it's just an optimization. So CUDA 6, our recent release, production should be coming out in a couple weeks. One of the biggest things we added was called unified memory. So, I mean, traditionally, what we look, we have two processors, right? We have a CPU and a GPU, or multiple GPUs, and they each have their own memory. Their own memory and their own memory spaces. For a while now, we've had unified virtual addressing, so they use the same virtual address, so you can use pointers around, but you still had to manually copy data back and forth. You had to allocate on the CPU, you had to allocate on the GPU, you had to copy and make sure they're synchronized in your code. And it added a lot of complexity and overhead just to get started, especially in C and Fortran. If you wanted to just try something, you had to do all this memory management first to get started. So with CUDA 6, we added unified memory, and this is true unified memory, where you do one allocation and use a single pointer. It doesn't matter if you're running on CPU code, whether you're running on GPU code. It synchronizes for you, copies data back and forth. Yes?
A single user pointer? In other words?
Yes, it is a single user pointer, correct.
Okay, so that means it's a virtual address, and all of the virtual to real translation is done behind your back?
Correct.
Ah.
Yeah, so it's copying around. It works with multi GPUs, so you can pass the pointer to run multiple GPU devices and copy the data. Yes.
Still, the memory units are different, right?
Yeah, so they're still physically different memories, but the software and the driver behind you is handling copying. It's doing it by page faults and stuff. It copies by page, and it's synchronizing. There's a couple points. Either when you launch a kernel, when you launch work on the GPU, it's synchronized, and then there's actually called the device synchronized API. It'll make sure the data is synchronized then. So it's not. This isn't a performance feature first. This is a productivity feature first. That was our first goal of this release, was just to make it a lot easier to get your code ported and running, a much simpler code. We will then start working on optimizations, making it faster depending on where people are using it, how they're using it, and working on that next. So, but our first goal for this was a productivity feature, getting people started quicker, making simpler code. So data movement is still an optimization. You can get in there and do it manually. Yeah.
So, in theory, this works with AMD CPUs?
AMD CPUs, yeah. Oh yeah, we support AMD CPUs, not GPUs.
I know.
Yeah, and we support ARM. We work on ARM too.
Okay, so that's pretty awesome.
What's the feature size?
The what?
Feature size.
The feature size. What do you mean
28 nano, 22 nano?
Oh, what's our GPU running at?
The feature size, the size of the transistor.
Yeah, on our GPUs, the latest public ones are 28 nanometer. I think the next one TSMC is doing is 20 nanometer. I think it's the next one coming out. Yeah, we're about a cycle behind Intel. With their fab, I think they're down.
But so is everybody.
Yeah, it's hard to keep up with it. Question?
Coordination is normally you can split the job up into chunks that don't interact. Can you now do interacting jobs like mutexes or software transaction management or any of these parallelism techniques that allow a task that wants to coordinate?
Are you talking about unified memory?
Yeah.
With this, it doesn't really add any benefits in that area. It's just managing the synchronization behind you. Still in the GPU, when you're talking, could be billions of threads. Synchronization's hard. And so that's why we do blocks. So you have blocks of threads that can all synchronize and talk to each other, but the blocks can't work with each other. There's no separate blocks. And so we have synchronization points where all the blocks will get to there, but different blocks could run at different times.
You have barriers. You all get up to the spot.
Yeah. But they're kind of coarse barriers. GPUs really have multiple levels of parallelism. That's like MIMD and SIMD and all different levels depending on where you're looking. So I mean, they're complex parallel machines. That's why programming becomes interesting.
So when you're talking about your mobile chips with the GPU on the die, is it still having to do this copying across?
No, it actually is smart. Since you're using the same memory space, so it does support unified memory, and we're just from a pointer using the same thing, but it could actually be using the same memory, physical memory.
There's no copying in that.
Unless it can't figure something out. It'll try to use the same copy. That's up to the driver to try to figure out if it can use the same one or not. And that's where you can get in there manually. You could still do it manually, the copying and which data you're going to be using.
I want to not copy.
Yeah, oh no, I understood, yeah. It's just, like I say, the driver may not be able to determine whether it can use the same bits or not. And so it may go separate, but you can profile that and figure that out and optimize it. But it will try to use the same actual physical bits if possible. All right, so that's unified memory, that's our big release. Real quick, just to show you what a CUDA C program looks like. Normally this is a lot longer, I'm just going to go through this one quick. Same function, that SAC speed, that for loop, y equals x plus y. So that's the CPU version, and that's the GPU version. Very similar. Let's go back. Same line. So in a CUDA-enabled language, you need to tell the compiler that you want to run something on the GPU, and so that's what in C it's __ global _. That's all you need to tell a CUDA-aware compiler that this is going to run on the device. You can call it from the host. And then you notice this I here. We basically have gotten rid of our for loop, and we're spreading the work across all the processors. If you've ever done any kind of 2D to 1D transformation, this is all this is doing. We have our block dimension, which is just the number of threads per block, times the block ID, and then we add the thread index. Because we just have all these little threads running this work. And that gives us into the input away. So this basically replaces the for loop. You always have our if check. Don't want to overwrite memory. You may have extra threads, just like a for loop. That's why we do this if check. I like to point this out because this is a very common mistake people make. They write their algorithm with the perfect data that evenly divides into their threads, and they go to a real data set, and there's some extra threads, and they start overwriting memory. Was there a question?
Yeah, what's the correspondence between blocks and threads?
So normally I go through a much bigger thing. A block is kind of the coarser level of parallelism. It contains a bunch of threads, and so blocks can execute at different times on a GPU, but when a block's running, all its threads are working. And so you could have, hundreds of thousands of blocks, and the hardware will just keep processing blocks until they're all done. And then the threads are the entities within the block that actually go through the code and execute the code.
Roughly how many threads?
It depends on the algorithm what you want to do, and this is where you can specify it in C, or the compilers will try to figure out for you, but usually anywhere from 32 to our modern hardware is 1,024 per block. So like on a high-end Kepler, we have 2,048 CUDA cores, or basically ALUs, that these threads are running on at a given time. Some of those are single precision, some of those are double precision. All right, so just real quick, run through this with 30 data elements, see what it looks like. So if I arbitrarily said I'm going to do 3 blocks of 10 threads each, I would do block dimension of 10. Is what just the read-only variable would tell us. So for the first block, index 0, 0 times 10 is 0. Then we have 10 threads. That's how we get I to go from 0 to 9. Block 1, now we have 1 times 10 is 10, and we add 0 to 9 to that. That's how we get I to go from 10 to 19, and so on. So this is how you would actually break up your code to work on different parts of your data, to take different paths. You can diverge if you wanted to, even though it's not always advised to diverge, but this is how you break up your program.
So roughly, what's the minimum problem size when you actually see a speed up?
So what's the minimum problem size when you see a speed up? A lot of it depends on data movement. Whether it's on the macro, and this is just computing in general, the macro level, moving data, or even within the transistors and the chips. Data movement's where we spend all our time and our power. Like computation nowadays is virtually free. And so if you were to do just these small Saxby example, it would be way slower than the CPU, because you're spending, you're doing 2 transfers across the PCI Express bus to do one really simple computation. And so that would be fast. And so it kind of becomes an algorithm where you have to weigh that data transfer time to the GPU, how much work you can move to the GPU, because move that data once and leave it there as long as possible. But you can also get a cycle going. You get what we call a pipeline. You transfer a little bit of data, you start processing on that, and then while that's processing, you're sending the next set of data, and then the results come back. So you get this pipeline, so you're hiding all that latency across the PCI Express bus. And this is where in the mobile space, where I'm getting to exascale, we're going to be moving processors onto the same die, so they're sharing the same memory, and so that PCI Express bus basically gets out of the way, that data transfer time. So you would want fairly big problems. It's really hard to give you an arbitrary number because it totally depends what you're doing, but you'd want fairly big amounts of data or a whole bunch of little ones that you can batch.
So libraries like NVBlast, they are smart enough to figure
out? Yeah, NVBlast will actually, and you can configure it, you can manually, but by default they will say, this is a really small problem, I'm just going to keep it on the CPU. And then it will move, if it's a bigger problem, and there's a configuration file where you can go in and modify it if you want, but it does that by default. All right, so how do you actually call this Saxby function from main? So I'm going to start with the same code on both sides and then just modify the right one. We have our pointers, and this got way simpler with unified memory. This used to be 2 slides of code. We allocate our size, we malloc our x, randomize it, do the same for y, randomize it, and call our function. So here now with CUDA-enabled language, we just replace it with CUDA malloc managed, and this gives us a pointer to x. This is an API call. I'm not checking the error code, it's bad coding, but it makes my slides simple. Randomize it, same thing for y, CUDA malloc managed. We modify our CPU call to now call the GPU, and we're using the same pointers. And now in C, we have these new syntactic element, these triple angle brackets. And this just tells the GPU, or the hardware and the software, how many blocks and how many threads per block we want. So that's all these numbers are doing. And again, like in OpenACC, the compiler's figuring this out for you. We're coming up with ways to get rid of this in C as well, and just make it an optimization. And then our free just become CUDA free. So that was all that was needed to actually run this program and run Saxby on the GPU. Again, unified memory made this way easier. Before, you'd have to do a CUDA malloc for a device pointer, and then CUDA mem copy the data over, run your code, CUDA mem copy it back, and it just was complicated and messy. And with unified memory, like stuff like linked lists and C++ data structures just work. You basically overload your new and your delete to use CUDA malloc managed, and then the C++ just starts working. All its complex memory management just falls out, and it's really awesome. Especially with linked lists, because linked lists were essentially impossible before because you had to do pointer traverses across the path plus. Yeah.
So is part of the unified memory that graphics memory now appears inside user space?
Graphics memory, no. This is a CUDA only technology, like for CUDA specifically. You can have CUDA and your graphics memory interop, like OpenGL and CUDA interop really well. But yeah, your CPU is not going to see graphics memory because we don't allocate that with CUDA.
Okay, I was just wondering if if you were serving lattes with the because that would be really nice.
No, so I mean, you could from a CUDA program, you can talk to the OpenGL memory that's being rendered. We actually have a number of samples that do that. It's very easily interop, but yeah, you have to set that up through CUDA to get that working. All right, so that was the programming languages. Lots of great tools out there. If you are going to be writing this stuff, highly recommend you use a profiler. And the whole point of going to accelerated computing is to go faster. If you're not using a profiler to tell you where to go faster, you're really doing yourself a disservice. We have debuggers, CUDA, GPU debuggers that are all visual. You can set breakpoints, step through them just like you do CPU code. Debugging, you can debug at the assembly level if you want. We have a great, what's called CUDA mem check. You're doing parallelism, so it checks for race conditions, but it gives you human readable output, like this source line is causing a read at this source line, go fix it. Fantastic tools. The profiler is really a really fun one to work with. It does a whole graph of when the data copies are happening, what kernel's doing what, in a nice timeline. So we have Insight as a plugin for Eclipse, and then we have Insight for Visual Studio. It does work with the free one, which I think is Express. We don't have 2013 yet, which we get beat up on all the time. We're working to get that in very quick, but all this supports Visual Studio as well. And these do allow cross-compilations, so on Windows you can compile for ARM. On Linux, we can't do Android yet from Windows, but you can compile that for Android from Linux. We're working on getting the Windows one working, but you can cross-compile. And we have remote debugging, so you can remote debug your Linux box running GPU from your Windows machine, which is pretty handy, especially if you're working on a cluster that doesn't have heads or no displays.
There's a question mark.
Yeah.
So your Eclipse version does not work on Windows, though, right? You've got
Correct. We do not support Eclipse on Windows. Yep. We get that request a little bit. There's just not a huge demand. If you are interested, definitely let us know. That's something we'd be interested in looking at. But most people who work in Windows don't use Eclipse. They use Visual Studio, so that's what we support. Yeah, that's just a shot of our profiler. All right, some more fun examples. Big data. So you guys want to hear. So these are companies currently using a lot of GPUs for. Salesforce, they're one of 6 companies that have the full fire hose, Twitter fire hose turned on for them. So they get every single tweet. I think it's like 450 million tweets a day. One of their features is to do real-time keyword search. So you can just search and see what's coming in on the Twitter feeds. You get them popping in. And with that 450 million number, they just were not able to keep up with a traditional CPU cluster. They just couldn't do it. The clusters were getting massive, really expensive, and just with all the communication required, they just couldn't keep up. But by moving to GPUs, they shrunk their cluster way down, and they're actually back to real-time search now, as close to real-time search as they need to be. That's just by taking all that data and dividing them up on all the processors available on the GPU, sending that data out, and they just are really good at big data. Shazam, anybody use Shazam in here? I make Shazam all the time. I see all the younger people nodding. Shazam's an app for the phones where you can, say you're listening to a song and you want to know what it is, you hit it, you tag it, and so it listens through your microphone for 5-10 seconds, and then very quickly comes back with the song, who it is, the artist, that exact version of it, and then you can buy it, all kinds of other stuff. But they're doing 350 million tags a day. So people just listening to songs and tagging it, and when you think about it, it's really incredible. On your car radio, you hit it, and within 10 seconds, you know what that song is. And so what it's doing is it's recording a little soundbite, sending that to their servers, comparing of all the millions and millions of songs they have in their database, going through each one and checking that little soundbite against all of them until it finds a match. And again, they were a big CPU cluster, kept adding more and more money, more and more power, and just couldn't keep up. But by using the right processors for the job, going to this heterogeneous computing, they shrunk their cluster way down and are able to actually keep up with demand now. To the point where they're going to add a feature where you can just turn on Shazam all the time on your phone. And then so at the end of the day, you could go back and just see all the songs you happen to hear or be walking by. So apparently some people want this feature. I thought it was kind of weird. But it's a feature they're going to do now. Visual shopping, this is a Cortex that does something cool like say you wanted something like your couch to look like this carpet, I don't know why you would. You could take a picture of it, and it would go and find everything it can find actually in the eBay database that looks similar to that carpet. You know, especially like if you're into clothes shopping, you can do this with clothes. You wanted to match a dress or something. And again, it's very quickly back. You like 5 to 10 seconds, you get the results back, and you can start scrolling through them all. This is just perfect for GPUs. It's exactly what they do really, really well. And so they were able to get this service out. I think they started on GPUs. Finally, elemental ESPN, real-time video delivery. So now, if you go look at the mobile space, video delivery is actually a very hard problem because you have so many different resolutions and formats that people want to watch in, and you don't want the translation and transcoding to happen on the device because you kill power. And so places like Facebook and all these video delivery services, when they get a source video or picture up, they then go and transcode it and change it to all the different possible formats, all the popular ones, you know, like Facebook and Flickr. I mean, they'll have 40 copies of the same image so they can quickly deliver it to you. But by going to GPUs and doing this, that's kind of a big data problem. They just do it on the fly now, fast enough that they can do it on the fly. So they're not having to spend all the money on storage and all that extra processing power up front. They can just do it on the fly as they're being requested. Also, if you watch the Olympics, Super Bowl, anything, all those graphics, those are all done with NVIDIA GPUs. It's not just graphics; they're also doing all the image recognition and finding out where on the on the racetrack, on NASCAR, whatever, to put the arrows coming down, or all those graphics. So, lots of big data examples. That's becoming the big buzzword of the day.
So,
oh, my favorite one, yeah.
For the examples you quoted for big data, do you know if these coexist with the usual warehouse computing technologies like Hadoop and Storm?
Yeah, there's definitely Hadoop GPUs, GPU versions of Hadoop that work really well. There's a number of actual databases being built entirely on top of GPUs. That basically there's the core processing power of the databases, and actually they work really well. They're still kind of the researchy phase. They're making their way into commercial areas, but a lot of research being done in that area.
And are these like custom hardware or some commodity hardware?
No, just commodity hardware buying, building a cluster of a standard desktop with our GPUs and CPUs.
There's a version of Hadoop which runs on GPUs?
Yeah, it makes use of GPUs in the systems. Yeah.
What is it called?
Off the top of my head, I couldn't tell you. I think if you just internet search Hadoop GPU, I think it's out there. All right, so this is my favorite use of GPUs. I end with this. It's not a big data problem, but I just love this one because I hate mosquitoes. Apologize if you like mosquitoes, but see a few of them get shot down here. So this is a project to fight malaria in third world countries. Traditionally, mosquito nets have been the best choice. Yes, this is by Intellectual Ventures. I think of it up here. I know they're patent troll, but the science behind this is really cool. The project is very cool. So what they would do is, like, say you had a hospital you wanted to protect. You would surround the hospital with like these 12-foot wooden posts, because apparently mosquitoes don't fly higher than 12 feet until evolution takes over. Between each post, you'd have a really low-power laser grid. And so anytime something broke the grid, whether it was a mosquito, a bird, a dog, or a kid, it would then use a webcam, an off-the-shelf webcam, to do an image detection and detect A, that it was a mosquito, and B, that it was a female mosquito, because they have a faster wing beat, and they're the only ones that bite. So once they determined that this object was a mosquito, then they would use a more powerful laser and shoot them down in real time. It's the kill shot lasers, the Blu-ray laser discs. They're trying to make this cheap, so it's all off-the-shelf components. They're using laser printer components to actually move the laser to target it. But they needed to be cheap and power efficient. And so, here, I'll answer your question when we get through this. So they need to be cheap and power efficient. So they went to GPUs to do both the image detection, because again, it's exactly the reverse of what GPUs do, just consuming. And then doing the targeting algorithm, actually determining where it goes. There's a really cool TED Talk on this where they cover it, and then while he's on stage, they have a glass box of mosquitoes, and from 15 feet away, they're like tracking it with a little green laser as it's flying around. It doesn't kill them. So what's actually happening, they think when it hits them, it just kills them instantly. It like messes up their DNA. The wings burning off is just kind of a bonus after they're sorry, I hate mosquitoes. I'm from Minnesota. This hasn't really taken off. I think part of it is just they couldn't get the power requirements down. I really think our mobile chip coming out is going to make this type of stuff very, very interesting. Because now you're talking about massive, way more processing power than they were using at, like at a watt in this tiny little processor. I think we're going to see a lot more of this stuff. This is probably not in the US because you have the liability that you actually hit somebody in the eye. So I think it'd be awesome to have one of these like on a turret at like a barbecue.
Yeah.
You have little kill counters, be like a good scientist.
It'd be great for backpack games.
Yeah.
You can crowdsource this as a game, I'm sure.
Oh, easily, yes.
That might be offline
Kickstarter project. Anyway, this is my favorite use of GPUs to date still. Still waiting for one to top this. All right, so GPUs in the cloud is another thing I was told to talk about. So Amazon has lots and lots of GPUs in their cloud. So they have their G1s, which are their originals. They've been out for about 2 years now. They use our older Fermi GPUs, still pretty powerful GPUs. Each one of these instances has 2 Fermi GPUs in them. And they just recently added these G2 instances, which were mostly meant for graphics virtualization, for delivering graphics. So just as an example of this, we have our little handheld console called the Shield we make, a little gaming console. But you can actually stream games to it remotely, and like it works really well. Like I play it all the time at home from a server. So I'm in Colorado on a server in California. I can actually stream real time, and the lag, our goal for latency is the same as if you were playing on a console in your living room. And so that's all I play on there is games on the game streaming games now because it's rendering on a really high-end system, so I get a high-quality game and just on my little handheld console. Really cool. So that's what they're intended for, but you can also use them for compute, fully compute capable. This is actually, we have 2,100 hours of hands-on training at GTC going on all week. And so that's how people are doing it. They're remotely connecting to these GPU instances. So there's lots of them out there. If you've anybody used the Star Cluster, heard of MIT Star Cluster software? So a very cool piece of software. It's called Python, or built on Python. And it's for creating a dynamic cluster in the Amazon cloud. So you basically say, I want these type of instances. I want this many. Go build it. And it just usually goes off for 10 minutes, and it sends you back a SSH to a head node. You say, all right, here you go, start submitting work. But it dynamically contracts and it extracts, or expands, based on demands. So if there's no demand, it will shrink them way down so you're not spending money. And you can even set price caps on the instances, saying, I don't want to spend more than this. And so then if a bunch of work comes in, it'll start spinning up more instances to support it. Really cool piece of software. So if you're interested in quickly building a supercomputer in Amazon's cloud, something to look at. And then, yeah, we already talked about all our attendees going on. So we're doing 200 attendees at a time. So I know they have a lot more than that, but we don't even know. They're very tight-lipped about that stuff. So lots of GPUs in the cloud. There'll be more coming, hopefully, soon. So resources, where do you go to learn more? developer.nvidia.com/CUDA zones is kind of the primary link to remember if you can't remember anything else. Really good blog, Parallel for All by Mark Harris. He's our chief GPU technologist. I created a series called CUDA casts, which are little 5 to 8 minute screencasts. If you're more of a visual learner, just how to use the tools, what new technologies, how to use them. So that's on there as well. So if you're interested in technology, I suggest you subscribe, RSS, or email, so you can see when new stuff comes out. I've created a bunch of these self-paced labs. Right now they're very introductory. We have a lot more advanced ones coming. These are 90-minute, actually using the Amazon GPU instances. So it's all from within your web browser. You just need a supported web browser, which is basically anything except IE9 and earlier. But you get in there, you actually get to write code, execute it on the GPU server, try it out. There's CUDA Python for everybody wanting to try Python. I have a few Python labs on there.
Is this the class? NVIDIA-QuickLab.com?
Yeah, quicklab.com, NVIDIA.QuickLab.com. QuickLab is a third-party company. This is where Amazon does all their hands-on training through. We started working with them. Really great company. Still pretty new. But yeah, you can go try those out. Any documentation you want, whether you're using anything, basically anything of ours, go to docs.nvidia.com. It's all there. And then technical questions. So we have our forum, it's a good forum, but I honestly recommend everybody go to Stack Overflow. If you write any kind of programming, Stack Overflow, you need to know about Stack Overflow. It's like the place for programmers to go. The way I say it is there's like a few really smart people who, RTFM actually read all the documentation, and then they translate your questions into answers. So it records everything. I think we're already at like 4,000 plus answered CUDA questions. So likely if you're starting and you have a question, somebody else has had the same problem, go search. It's probably already there. But any kind of programming, you're doing SQL, Linux administration, Stack Overflow is the place to go. We have a registered developer program. We try not to make this a spam system. This is our way of telling you about cool stuff happening related to what you're interested in. So machine learning, data mining, all that. You tell us, and if there's webinars, we know there's conferences coming up about it related to GPU computing, we'll tell you about it. Again, we try not to make it a spam machine. You do get early access to all our software and certain library releases. We do like around GTC, we do a lot of stuff with our registered developers. It's free, easy to get in. So if you're interested, I encourage you to register.
So,
question?
Libraries like CUDA, are they ready to use for commercial? Can be used for commercial purposes?
So yeah, our CUDA toolkit's free. There are features of cuBLAS called Premier. This is actually new in CUDA 6. We have these Premier features, which enables a lot more things, which you can get a license for, you have to pay for. You do get early access trial licenses as a registered developer to try them out. The base operation of all of them are all free, like all our toolkits all free. But like I said, with like multi-GPU support above 2 GPUs now is a license thing. You have to actually buy a license to use it with our compilers or with those libraries, but yeah, you can look up on the website. It has a lot of details on that. GPU test drive, I'll just mention these guys. I mentioned this to you. If you had code you wanted to run, this is essentially you get access to a supercomputer, all set up and ready to go. You just say, I want to try this. You get a SSH access for a day or two to actually go out and run code if you wanted to try something. So, you know, big, nice supercomputers, latest hardware, just so you can see what speed ups you get. And our conference. This is our conference. It's growing bigger every year. I think we're 45% bigger this year. Just kind of the exponential growth more law. We're happening right up here in the convention center. It started today, very little, but most of the stuff's going to happen Tuesday and on. You know, we're up to 500 plus sessions covering the whole gambit from robotics to machine learning to oil and gas to finance, and everybody's there. So this is kind of the place to go for GPU computing. If you were to get started, my 5 steps, try out GPU computing. This link has all our how-tos of getting started for all the different languages. Subscribe to the Parallel for All blog. It's a really good blog. We really try to keep the marketing side of it out of it, just keep it technical. Sign up as a registered developer. Again, try not to spam you. You can always opt out of the newsletter. So, install the CUDA toolkit. It's free if you have a GPU. Give it a shot. And then you can either attend GCC 2014, or I think somebody mentioned we do record everything possible that we can publicly record, and we make it available within a week or two after the conference. And we have done this for every conference we've been a part of since 2009, I think, Supercomputing, International Supercomputing. So you can go search through it all at that same website, nvidia.com/DTC. So if you're interested in like R, there's a bunch of talks on R on there, you know, in-depth library talks. So it's a good place to go to learn more. All right, any more questions?
Does CUDA work with competitive GPUs? AMD or Intel or anybody else basically?
Say it again?
Does CUDA work with competitive
Does CUDA work with competitive GPUs? No, CUDA only works on Nvidia processors. We did open source it, so it's possible. PGI made a CUDA x86 compiler, but they didn't find, nobody wanted to do it. So they're like, why would you run that on an x86? So they did it as a toy example, but no, right now it's just Nvidia GPUs. But that's why we have OpenACC, because that's a very portable. The OpenACC directive, that is very open. It runs, the compilers support all the major accelerators.
And what's happening on OpenCL front?
So OpenCL, we stopped at 1.1. We support that for legacy purposes, but we are currently not supporting OpenCL 1.2. There's a huge demand. We might change our roadmap and the way we go, but right now we just don't see the demand to do it. Yeah.
In the Saxby example, it appears that each core is doing a single floating point multiplying math. How general is what?
Yeah. So the question was, in the Saxby example, I'm using one core to do one operation. That's not very efficient. It's for the simple case for here. Typically, you'd want to do a few more operations per core to help with like memory fetching and get that pipeline going within the chip. That's where our profiler will actually tell you that. It'll say you're memory bound. You need to add more operations per core, or it'll walk you through in human readable terms how to optimize your algorithm to make it more efficient. But yeah, that case is not very good. It's for an educational purpose only. Yeah.
Does everything you discussed apply to consumer Nvidia GPUs as well as the Teslas? If not, which?
Yeah, so CUDA runs on every one of our GPUs we've sold since January 2007. So GeForce, Tesla, all those. Yeah, Tesla ones are going to be a lot more stable. They usually actually don't run as fast as GeForce cards, because in GeForce you don't care if a few of your pixels are off, once every 60th of a second. But on a Tesla card, if you flip a bit or something wrong, that's bad in your your computation results. So the Tesla cards are more expensive, but they also come with a lot more support. They've probably had 24 hours of testing done on each card, whereas a GeForce card maybe has 5 minutes. Just because they're a lot cheaper, and they're meant for gaming, right? They're not meant to sign. So a lot of people will try to go the cheap route and get GeForces in their clusters, and it works for some people. The other problem is GeForce cards quickly get end of life. The third-party companies that make them. So if you have you buy a whole bunch of them, and one goes bad, you can't get a replacement. That happens to us a lot. Whereas the Tesla cards are long-running; they last a while. So it's the toss-up whether you want to go the cheaper route.
Well, okay. Since you mentioned that, how problematic is it to mix and match these things? Like if you get like if you're building a cluster and you want to upgrade things, like you want to use, like say a new Tesla model comes out and you have already existing Tesla cluster, you want to add a new Tesla, is it going to be okay to? So
yes, the question is how hard it is to mix and match GPUs. It's about the same as mix and matching CPUs, right? You can make it work. It's just going to be more work on your part, being able to see which GPU is and allocate it correctly and optimize it correctly. The same as you've got a cluster of different types of CPUs, newer generations versus older generations. Some features are going to work on the new ones and not on the old ones. The new ones are going to be faster, so you have to optimize your whole cluster setup for it. But yeah, it does work. You can do that. Any other questions? Yep.
you mentioned that if we're using GPU for graphics and for computing, and the graphics is always a higher priority, is there any way that if we want the graphics be lower priority?
So that's a question coming up, basically being able to set affinities or priorities on the processors. So we've looked at that. A few people asked that. It's most of the time there's not a lot of benefit to that, like dropping your display. Usually what you do in that case is either, I mean, if you really want to do it, you could go to a software renderer and then just that get better, or put it just a really low user-integrated GPU or something to drive the display. It's just not a big use case we've seen.
How does CUDA relate to PhysX?
How does CUDA relate to PhysX? Basically, PhysX was rewritten in CUDA. We bought the company that did PhysX. They had a separate hardware chip, and we basically took that chip and implemented it in CUDA, and it runs on the GPU.
Second, what's your email?
What's my email? I will have cards up here. Yeah.
Yeah, so I was wondering, although Intel and Nvidia are the basis of many supercomputer platforms, Intel doesn't like sharing.
Right.
So although you have a superior product, they're going a different way. Could you comment on the relative merits of Tesla versus Xeon Phi?
Yeah, so different merits between Xeon Phi and Tesla. So first, we've been in the industry a lot longer, so we're a lot more mature. It's just
yeah.
Xeon Phi, there's a slightly different way to program it. Same idea, massively parallelism. What else? They are trying. They don't like to share. They're looking at going with Knight's Landing and taking some of their Xeon Phi cores and putting it on the CPU die, and then just basically getting rid of the PEX bus, which is an interesting approach. I think we're going to have to do something similar to get to exascale. A lot of companies don't like that, and the same reason they don't like using CUDA. They don't want to be all Intel for everything. They don't have locking everybody else out. So a lot of companies are not happy about that, especially in the government space. So I think we're both trying to solve the same problem, how we're going to get to exascale. So I think it's going to be the same kind of combination. I think GPUs are going to pull in some serial processing cores, CPU cores. There's probably going to be something that replaces the PEX bus, gets rid of the PCI Express bus, and more customized systems. But it's going to be a very interesting problem going forward. But their Xeon Phi it works. In my opinion, it's a lot harder to program. They touted their recompile and run, but it's just not true. It's the same thing. You use libraries, you use directives, and you use their vector intrinsics to program it. That's the way you program Xeon Phi. Does that answer your question? Do you want me to go more details?
So what I was kind of looking at is, like, we have 4,000 cores. They have maybe 400 cores, and on an aggregate throughput basis. But so, I was kind of looking for something which says, like, if you need your cores to talk to one another, Xeon Phi is a little better, and if you don't need them, we're way more computational or something like that. So a use case that would showcase.
I don't think there's been a use case that Xeon Phi has really excelled at as far as like a real world application. There's definitely some ones you can come up with, but as far as like those 272 applications I put in, there's really not many that Xeon Phi just takes off and blows us out of the water. They're catching up. I assume their next release is going to be much better because this was really their first accelerator that came out. But yeah, as far as communication, it's very similar. It's a massively parallel, so you offload your massively parallel. There's a lot of extra computation that you need. You need a lot of those synchronizations. It doesn't work as well. That's something that's very data independent, embarrassingly parallel.
And something about the double precision units. For example, I think last time I checked, the Nvidia GPUs had one per block rather than, they had roughly double the number.
So in our high-end cards, we have, I think it's 64 double precisions to 192 single precisions. Is that right? Something like that. So we have a lot more single precisions. Essentially, in our high-end card, we're I think at 1.4 teraflops of double precision performance. That's the peak for a single GPU card, and whereas single precision is about 4 times that. It's around 4 teraflops single precision.
To piggyback on this question about the Intel guy, AMD guy, what about IBM guy? Which one did you use?
The IBM guy.
Yeah. So you have this question.
Oh, for programming?
For a comparable product. You're talking about
so IBM doesn't have an accelerator. That's why we partnered with them. We're going to now be building their supercomputers with their power core, CPU cores and our Tesla GPUs.
Aha!
Yeah.
That's why you're part of OpenACC Power.
That's one of the reasons.
All right.
Yeah, so they'll basically all their new supercomputers coming out will have our GPUs in them, which is why they're moving their Java their whole Java suite to be accelerated. Any other questions? All right, I like that. Thank you.